From Imperial College London, welcome to this special lecture vodcast.
Good evening, ladies and gentlemen, and welcome to this evening's 19th annual lecture for the Faculty of Natural Sciences, held in honour of Erwin Schrödinger. Now, if you remember, Erwin Schrödinger was an Austrian theoretical physicist who contributed to wave theory of matter and other areas of quantum mechanics, and he won the 1933 Nobel Prize together with British physicist Paul Dirac. Now, Schrödinger obtained his doctorate in 1910 and then accepted a research post at the University of Vienna, second Physics Institute. And in 1921, he left there, he went to the University of Zurich, where he produced papers that gave the foundations of quantum wave mechanics, which is now known as Schrödinger's cat. But it was during this period in the 1920s and then in 1926 where his great discovery, the Schrödinger wave equation, was made at the end of that period, and for which, of course, he got his Nobel Prize. In 1927, he then moved to the University of Berlin as Planck's successor, where he worked with Albert Einstein. But it was during this period that Hitler in 1933, of course, came to power, and he was unable to stay in Germany at that time because of the persecution of Jewish people become a national policy. And in the 7 years following that departure from Germany, he worked in Great Britain, he worked at Oxford, he worked in Belgium, he worked in Austria, he worked in Italy. He was offered a full-time position at Princeton, but said no, he didn't like America, so he went. In 1940, he went to the Dublin Institute for Advanced Studies, and that's where he stayed for a long time. He remained in Ireland for the next 15 years, doing research both in physics and in the philosophy and history of science. And of course, it was during that period that he wrote What is Life?, showing how quantum physics can be used to explain the stability of genetic structure. After his retirement in 1955 from Dublin, he returned to his native Vienna, where he died in 1961. Now, this is the only prestigious lecture that we hold here at Imperial for a named scientist who never worked or actually studied here at Imperial College, although obviously his work has had a direct impact on most of us who work here. And this evening, I'm delighted to welcome Sir Harry Kroto as our guest speaker. And Harry, following an early education in Bolton, soon realised that he had to escape and got over the border to Yorkshire quite quickly. And it's quite interesting because when he left school, he went off to the University of Sheffield, because that's where they said the best chemistry was done. It was probably true in those days. To do chemistry. And on his first day, he walked past this big building that said the Institute of Architecture. And he thought to himself, God, I never knew they did architecture at university. Otherwise, that's probably what I would have done. So it's a good job he knew nothing about architecture. But it's interesting tonight that his talk is entitled Architecture and NanoSpace. So it's still there in his brain, presumably. Now, having received his BSc and PhD from the University of Sheffield, he went on to do postdoc work at the National Research Council in Canada, then the Bell Labs, the famous Bell Labs in Murray Hill, New Jersey, and then after that started his long academic career at the University of Sussex in 1967. He became professor in 1985, Royal Society Research Professor in 1991. In 1996, he was knighted for his contribution to chemistry, and later that year, of course, with Robert Curl and Richard Smalley, received the Nobel Prize for Chemistry for the discovery of C60, but amongst the fullerenes that you see here, a new form of carbon. Now, Harry is absolutely passionate about science, and one of his aims is to excite and stimulate young people to be interested in science and ultimately study science. And he himself tells the story when he was at school. He lost chemistry, of course, because it created bangs and explosions and he blew up the kitchen and all sorts of things. And that's just what kids don't get access to anymore today. But to help him in this aim, he set up the Vega Science Trust in 1995 to create science films for broadcast on network television. And it produces high-quality films which really give the excitement of scientific discovery and also explain the intrinsic concepts and principles without which, of course, fundamental understanding of science is impossible. So it's a great pleasure to have Harry with us tonight. He travels a lot, he works hard, and it's just a very, very difficult person to get hold of, but it's great that we've managed to get him here, and so we're very interested in learning much more, Harry, about your chemistry. Thanks very much.
Well, with that sort of applause, I think I'll leave because I don't think I can get any better than that. Thank you very much for a fantastic introduction. And Peter, thanks for the invitation. And so lots of good friends. But one reason for going to Sheffield was George Porter was there. And Lady Porter is here in the audience. Fantastic to see you back. And there are other people in the audience. And one is Mike Mayer, who's here at Imperial. I don't know why he's at Sussex, but there you go. He's here at Imperial. It's a pleasure to be here and to actually give this lecture in the name of Erwin Schrödinger. I could do with some more noise, and let's turn that up a bit because I want to get some. I have to waken up myself. Okay, yes, that's better. Well, I'm actually now in Florida. The US isn't quite that bad as far as I'm concerned, but sometimes gets worse, you never know. But we spend about nine months, my wife Margaret's in the audience here, and we spend 9 months a year over there in the summer months back with civilization back over here. But anyway, before I ended up in Sheffield, I thought I'd show you what I was doing at school, and in fact, you might recognize the guy in front. We were at school at the same time. This is when he was on Broadway. This is what he looks like now. And the thing is that I taught him all the acting he actually knows. And I thought, let him do it. I'll do some science. Anyway, Ian and I are in the same year. And in fact, I think this year is his Lear year. And we're going to have a reunion in Stratford. All the kids who were in Henry V at school are going to get together, and it's going to be a very exciting time. Anyway, the other, whoops, well, that was fast. One reason that I'm a scientist is that, as many of you know, 2 times 3 is equal to 6, hopefully. 3 times 2 is equal to 6, and that numbers commute, and that sometimes A times B is not equal to B times A. If you want to understand really what's going out there in space, you really have to understand quantum mechanics, and it's wonderful this is Schrödinger lecture. And in fact, basically, when an electron drops to a lower level, the photons that are emitted and are absorbed by the eye, if you really want to understand what's going on, you do have to know something about quantum mechanics. And much of it is embodied in this paper by Van Vleck, which says that practically everyone knows that the components of total angular momentum of a molecule relative to x, y, z fixed in space satisfy this commutation relationship. Now, as I was walking onto the campus here, I was asking a few people whether they knew this. Richard, I'm afraid there were not quite as many as you might like. But anyway, why should one actually know that? And the reason is that the Earth orbits the Sun, we use classical mechanics, but when an electron orbits a nucleus, you use quantum mechanics, and associated with this, the angular momentum are numbers, and don't worry too much about those. But when J is equal to 1, there are 3 orientations, up, sideways, and down, okay? So when J is 1, 2J plus 1, the number of orientations is 3. When J is 0, the number of orientations is 1. When it's 2, it's 5. So 0, 1, 2 maps onto 1, 3, and 5. Now, some of you may not be good at maths, probably because you're physicists. And so for you, we got to get those physicists sometime, you know. Anyway, I'll throw away the numbers and put in some boxes. And now I'm going to double up the boxes, okay? Move them together. Move that to there, this to there, this to there. Double that one, double this one, double that one, that one. Move this to there, and what have we got? Does nobody know here? Okay, yes, it's the periodic table. Now, what is fascinating, what I think is beautiful, and what science is all about, is the periodic table is really based on the numbers 0, 1, 2, 1, 3, 5, 7. It explains the whole of chemistry, all of biology and life, and all the useful bits of physics, if any. All right. But of course, obviously, chemistry is a major subset of natural science and physics. But when I got, I was at Sheffield and learned spectroscopy, and then went to Canada for 2 years, and then went to Bell Labs for a year, and then came back to Sussex. And there I was really fortunate. I had some great friends and managed to get started and do some nice work. And I thinking, well, if it doesn't work, I'm going to go into graphics and art and stuff like this. But anyway, things started to work. And one thing is that I started to sort of study molecules which were interesting from a point of view of radio astronomy. And the molecules that I worked on were these carbon chain molecules, sort of atoms in a chain. And as they rotated, they give out sort of light. And when they vibrate, you can observe the vibrations. And with quantum mechanics, you can actually study the rotations and vibrations at the same time. And in fact, Mike, you will recognize this because Mike Mayer, who's in the audience, and now I think he's a neuroscientist. I don't know how he managed this, but he actually wanted to, as I remember, wanted to row in the boat race. I mean, that was the one reason. So he decided to do medicine just to row in the boat race, and something like if he could. But anyway, he's now here at Imperial, and it's fantastic to see him again. And we studied these molecules, and if you actually look at this, you can see the radiation frequencies. And it turned out about the same time that we made this molecule. And Charlie Towns, who got the Nobel Prize for developing the laser, used radio telescopes to look out into space and these black clouds that are smeared across the sky and show that you could see molecules in them. This is a big breakthrough, a massive breakthrough, that these black clouds that were smeared across the sky were full of molecules, okay? And it turned out that this molecule with 3 carbon atoms had been detected, and we had made this one with 5. And so it wasn't sort of too difficult to say, well, let's try and look for this. And I sent it to Takeshi Oka, as a Japanese scientist, fantastic guy, and one reason why I nearly left science, because I decided if I've got to be as smart as this guy to do science, I'm getting out and doing something else. But anyway, I didn't do that, and we had this molecule, and I sent a letter to Takeshi, and it sent this letter back, and if I blow this, it says, thank you for your letter. Yes, I am very, 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 very much interested in your molecule. There were as many verys as there were carbon atoms in this molecule. And we got together, and we detected it using this telescope. This is the telescope in Algonquin Park. And this picture was taken in the middle of summer. And if you've lived in Canada like we have, you'll know that it takes a long time for summer to turn up. Anyway, we used this telescope, and we pointed out in space, and we actually saw these carbon chain molecules there. And then we synthesized this one, Dave Walton and Colin Kirby, and we worked on this molecule, and we detected that, and we in fact detected all these carbon chain molecules in space, and that was very exciting. And here is a picture when I used to have hair. I'm the guy on the right-hand side, not this guy over here. Lorne never had any hair, even when he was born, I think. But anyway, Lorne Avery, Takeshi Oka, Norm Broughton, and John McLeod. These were the guys, and it was really exciting in the mid-70s to detect these carbon chains. And to give you an idea, the Brighton Evening Argus said, the chemicals were discovered thanks to Canadian work in radio astrology. Okay. Well, there you go. But at least at Sussex, we did research. You know, you see that. Anyway, so that's the newspapers for you. And that was very exciting because we'd actually found that there were some really big carbon chain molecules in space. And then a little bit later, about 1980s, people started to look at stars that were blowing up. And in fact, we now know, of course, hydrogen is squeezed into helium, 3 helium nuclei into carbon, and carbon, helium to oxygen. And all the carbon, nitrogen, oxygen in your body was once inside a star. And millions of years ago, the star blew up, blew your atoms out into space, floated around in space, and ended up on the Earth. And in fact, we all came from outer space. And in fact, you're lucky to be here. I often ask little kids, do you want to see an alien? And they say, yeah, yeah, yeah. Well, I just say, well, really look in a mirror, because you are an alien. In fact, one day the sun will blow up, and it'll be hot, even here. But let's be optimistic. Let's hope the sun gets us before they do. Okay, whoever they are. But in fact, you're lucky to be here, because most of the carbon is still out in space. Most of the people who could be here are still out in space. And there are a lot of people around that I think we should send back out into space as well. Anyway, there's a whole story of C60, and I'm not going to go into that because it's a while ago, and many of you know the story. But basically, what happened is we tried to simulate the conditions in a star, and we vaporized carbon, and this molecule turned up. And, I started walking down the street, someone lobs a football into my hands, and I'm looking, it's a football. Gee. And Rick and Bob and the students, Jim Heath and Sean O'Brien, Yuan Liu, and they gave us a Nobel Prize for that. Just, there you go. But anyway, there are basically now 3 forms of carbon. There's basically diamond, graphite, and C60, Buckminster fullerene. My main claim to fame is I named it after Buckminster Fuller. My son said, gee, Dad, the only thing you actually did is made Buckminster Fuller even more famous than he was before. You need your children to really bring you down to earth. Anyway, that was exciting, and there's a whole area of fullerene chemistry. Perhaps the most important aspect of the discovery of C60 is that sheet materials like graphite will curve into balls or into tubes. And in fact, boron nitride has a similar sort of form to graphite, and it forms tubes like this, nanotubes. So of all the things, that perhaps the most important aspect of the discovery is that if you have sheet materials on a nanoscale, on a small scale, they will, in general, close up. Molybdenum sulfide does it, boron nitride does it, carbon does it, and that's the important fundamental discovery that we made. In fact, you can make big carbon chains like balls like fullerene, such as this one, which is about C240. Perhaps as interesting as anything else is not only C60, but you can actually stabilize some of the smaller ones. For instance, by adding hydrogen around the sort of waste of C50, which is unstable, you can stabilize it. And in fact, we wrote a paper, Dave Walton and I wrote a paper, that if you added sort of 10 hydrogens to C50, it would be stable. And the paper came out a couple of years ago, which showed that if you add 10 chlorines, you could actually isolate this molecule. So this paper came out, and I was so excited. Here was, one of the nicest things I'd done recently. And I sent an email to the guy. Oh, well, actually, I looked at the paper, and we weren't there. That really pissed me off, first of all. But then I sent an email saying, look, you should look at this paper. We predicted that this would be stable about 10 years ago. And I got an email back saying, yeah, we knew about your paper, but there wasn't enough room to reference you. So I didn't leave enough room on this slide to reference everybody. Anyway, that was a funny email. But it is now clear that you can make carbon cages and stabilize them by adding hydrogen. In fact, dodecahedrone, which is a C20 cage, if you add 20 hydrogens, it actually is stable. And it was made before we made the discovery. And now we will see a dodecahedrone. Those who are chemists know that Louis Paquette made that. We would see that as a cage system, a fullerene that was fully stabilized, so it's known. You can actually make little thermometers, in fact. These are tubes of graphite in which there's tin on the inside. In fact, it looks a bit like a thermometer. And in fact, a group in Japan, Bando's group, have actually made a whole set of these with indium and other things, and they raise the temperature and they look at it under the electron microscope and they see it moving backwards and forwards. But, you know, if you've got to switch an electron microscope on in the morning just to find out what the temperature is, it's a bit difficult. But it is possible now to make devices on a nanoscale, such as thermometers, many other things like this, which are showing us what nanotechnology actually is. Okay. You can put iron on the inside. Here are some tubes of carbon. The green is, imagine that you're looking at a cross-section of a tube. The green is carbon, and there's iron on the inside. And if you had a cluster of iron that was that size, it would just oxidize just immediately. But by wrapping it in carbon, you can actually stabilize it and look at its magnetic properties. So you can use these carbon tubes as nanoscale test tubes for small clusters. And that's a major breakthrough as well. Well, how big are they? Just to give you an idea, this is a carbon fiber. Imagine the carbon fiber is very thin, about half the width of a human hair. If you snap it, as this has been snapped, what has been found in a certain type of these fibers is that coming out of the center of it is this nanotube. Gives you an idea of the size. This is a carbon fiber which to some extent has revolutionized materials. But if we can make those nanotubes, we'll go to the next step in revolutionizing materials. In fact, if you can make a bundle of these, a bundle of 10 to the 15, you would have a material about 30 to 50 times stronger than steel and 1/5 the weight. Some numbers like this. Because you could put them together, stack together with van der Waals forces, and they would be incredibly strong. But we still are nowhere near making them like that. But that's the future. Okay, so how small is a buckyball? Let's shrink the Earth down to the size of a football, okay? That's a factor of 100 million. And let's shrink the football down to the size of C60. That's another 100 million, 10 to the 8. So the ratio is 10 to the 8. It gives you, some people feel that. I feel it gives you an idea that buckyballs are bloody small, okay? And 10 to 8 is the last fundamental constant, so physicists can now give up because there's nothing else of any important, really worth knowing. I had this on very good authority. This guy actually told me that. Okay. Perhaps the most interesting application is just around the corner with C60. By doping plastic solar cells with C60, you can really significantly improve the electricity production of these plastic solar cells. And one reason for that is C60s are very good at capturing electrons, and what you need is charge separation. So that's an exciting possibility. And one of the aims of these new sort of approaches to solar cells is that hopefully we'll be able to use a printing press. Instead of printing the sun and all Murdoch's crap in his newspapers, maybe we'll be able to print it on solar cells, okay, and cover, you know, the whole of the Sahara Desert with something that we can pick up the sunlight. Or one or two states in the USA that don't think this science is very useful, like Kansas and one or two places like this. Anyway, basically, this is a very interesting technology that if you can use printing press technology to produce these solar cells, then you can actually make a breakthrough because silicon is just too expensive. We have to somehow break through, and Jim Barber and others, we were at a meeting yesterday in Milan discussing these sorts of issues. Supercomputers, well, if we can really get molecular electronics off the ground, we can take something like all this stuff and put it into a wristwatch. And this happens to be a Calvin Klein wristwatch, and it might actually be worth what you paid for it, you know. I mean, you just put CK on it and you pay 100 times what it's worth. It's fascinating. That's how easy it is to make money if you happen to be certain people like Calvin Klein. Anyway, this situation now is really quite interesting. We've got a carbon construction kit. It's hexagonal carbon, sheets of this. You can make C60, which is round. You can make C70 like a rugby ball. You can make small fullerenes, C28, this one. You can make giant fullerenes. You make nanotubes. You can make conducting wires. We've made some beautiful little conducting wires which are carbon on the inside and wrapped in molybdenum sulfide. So they're insulated, and these are possible electronic conductors in nanoscale electronics and molecular. We've made actually springs like this, which can actually compress out of molybdenum sulfide. So these networks are really very useful. They're flexible. They can make flat sheets, positively curved sheets, positively and negatively curved sheets, and somewhat more interestingly curved sheets. So where are we now? Well, Imperial College. Okay, chemistry is now overlapping with biology, with physics and engineering, and it's a very exciting, I think it's more exciting than it's ever been in many ways. Molecular biology, molecular electronics, material science, and they're all wrapped up in, if you wish, can call that nanotechnology. And I call that 21st century chemistry. That whole area is not so much that it's new, it's just a new recognition of its significance and its perspective. And in fact, I think no real progress in nanotechnology will really be possible unless we really do understand the basics of the chemical bond. And one thing, I mean, that great physicist Feynman said what the most important piece of information at some point was that there were atoms which, as they came together, they were attracted, and at small dimensions, bond lengths, they actually repelled, which was the essence of the chemical bond. And I think it's more important now, particularly that overlap with physics, that overlap with materials engineering, that overlap with biology, makes it more exciting than I think it's been in the last 50 years. Okay, so I want to now go to the second part of what I want to say. This is the molecule C60. When we draw it, or we look at this in general, we think of it like this. But in fact, it turns out there are two orientations. If we're looking at the molecule, and if we look at the molecule, which is C60 over here, next to it, we have two possible positions in the crystal. Either that double bond is in the middle of a hexagon, or it jumps to the middle of a pentagon. And I think this is perhaps the most important thing that I'm going to talk about. And that is, if you look at the crystals, let's have a look at this one, I think. At 200 degrees Kelvin, these molecules are moving. I think we've got to now think very carefully about molecular dynamics. And in fact, at 200 K, the C60 molecule is actually jumping from one position to another. And the point about that is that dynamics is important in the 21st century. Now, let me give you another example. One of my favorites is hemoglobin. The hemoglobin molecule, as you breathe in, it captures oxygen and hangs onto it, and then it has to move it to somewhere else in the body where it must release it. It's got to have this dual personality. It's got to be schizophrenic. It's got to hang on to as much oxygen as it can and grab it in the lungs and then release it where it needs it. And to do that, it changes its shape. And I think this fantastic result that Max Perutz obtained over 50 years ago is shown here, that what happens is there's the porphyrin ring where the iron, the Fe ion, as it captures oxygen, changes the size, and there's a histidine lever which changes the whole shape. And here we see the whole hemoglobin molecule changing. And I think what is exciting about the next 50 years of, say, the pharmaceutical industry is we're going to develop molecules with the degree of sophistication of this guy. And we're nowhere near that yet. When people say, you know, it's all over, you know, nothing new, let's try and produce a molecule like this that has this degree of sophistication. It can change its characteristics. It can actually do things. It's a molecular machine. And Max Perutz observed it a long time ago. This is nanotechnology in action. It's not new. It was developed by life millions of years ago. And we are still a long way, and I'm sure, Richard, you will agree, we can't produce a molecule that can do that from scratch, okay? But we shall do, and that is what nanotechnology is for me of the future, and it's terribly exciting. Well, you might think C60 is my favorite molecule, Mike might recognize this one. This is nitrous or ethane, and this is my favorite molecule because if you look at the microwave spectrum, and this is it, I mean, you may not be able to analyze this immediately, but Mike will tell you afterwards how to do it. You can actually show from this microwave spectrum that there's a structure. In fact, there's a sort of triplet standing out here and a triplet out here, and this doesn't quite look like a triplet, but nevertheless it is. And these two molecules are there in the gas phase, and you can separate them by spectroscopy and show there's a gauche and a cis form. Now, when we made this and studied it in the lab, I made this little model of it. And does it look like anything to anybody? Anybody? A dog. That's right. It's my dog. Carbon, hydrogen, okay? Blue head, red nose, okay? And it shakes its head. And this is the point. Looks at its tail. The molecule is dynamic. It does not just sit there, okay? Not only that, you know, it's been drinking. That's why it's got a red nose. And if you've been drinking, you know you've got a problem. And if you see a lamppost, it's quite useful. Okay. And Mike, I think you used to do some studies of this molecule, internal rotation. Now, the point about that is all those motions are things that the molecule does at room temperature. And I think it's now time that we recognize this. And I think in the next 50 years, we'll actually take advantage of this. And one of them I mentioned before is that we can actually make little shock absorbers. These are molecules that are actually dynamic. This is a molybdenum sulfide nanotube. And we've seen that it actually can absorb shock. And therefore, it's actually much stronger than we expected because it's a molecular shock absorber. What am I doing? Well, it turned out I had to retire. And Florida State at the time said, why don't you come over here? And that's where we are for 9 months a year, and 3 months we come back to Europe and to Sussex, where we still, and come home for Christmas as well. But it's interesting that carbon vapor is not just carbon atoms, but there are molecules like this in carbon vapor. Dave Walton, my colleague at Sussex, made molecules with about 32 carbon atoms, really in the 60s. And here, Dave is shown with a model of it. And what we showed that if you vaporize carbon, you can get these things, and you can get also the C60 molecule. Now, it turns out that Mike Bowers in Santa Barbara developed a really nice technique by ionizing these molecules and throwing them through a gas. And depending on the shape and the size and the mass, some things went faster than others. And in fact, if you looked at, say, a C32 signal, you ionize it, throw it through the gas, and it splits into 3 or 4 components, okay? So depending on the size. So here's C29, and there are 1, 2, 3, 4 different species there. And that's fascinating because this is carbon vapor. It's the most amazing vapor of all. There are at least 5 families. There are linear species, there are rings, ring 2, and full rings. We actually don't know very much about this. It's possible that these are monocyclic rings, and it turns out Mike Mayer's brother is, I would say, the best spectroscopist in Europe, and there are only 2 in the world who are competitive, and one's in the US looking at carbon, has shown that they're monocyclic rings. But all this stuff is not known, except maybe this group of fullerenes, okay? So carbon vapor, when you vaporize it, is full of fascinating stuff which we know almost nothing about at this stage. We can see species up to 1,000 carbon atoms. And it was this stuff that interested me in 1985. In fact, ever since I started with Richard Dixon and at Sheffield, an interest in carbon. And it's still not known. We found just one, that's C60. And that's what I'm working with at the present time in Florida with Alan Marshall, who's a genius at mass spectrometry. The other thing that I was interested in was the formation of nanotubes. Now, this is an igloo. This is a metal particle, and we're looking at a cross-section. So imagine you've got a bunch of tubes, and I'll show you in a minute, to try and understand how these form. And one idea I had some years ago was that if you have a metal carbide, on the surface of the carbide there would be surface reconstruction, and there would be segregation of carbon from the carbide and the metal. And just recently, with Florian Banhart, Mauricio and Humberto Terrones, who were students of mine some time ago, we've got some beautiful results. Imagine you have a metal sort of cluster, which is this green in the center, and we're looking at something in 3 tubes, nanotubes. If we took an electron microscope, what we would see is something like this, okay? So we see a cross-section of that system. What we've got here is this. We've got a metal iron sort of core, and these are the cross-section of these nanotubes. And this is the first time I think this has been seen, that this, you see that little cap? That's the birth of a nanotube. That carbon has somehow moved through the metal into that cap that's there. You can see it there. And in fact, little igloos of carbon are coming off. And I think this is one of the nicest pieces of work that I've ever been involved with, and I think it's the first time that anyone's seen the birth of a nanotube from a metal particle. So that's the sort of things that we're doing. The other thing I'm working on is I'm moving into a bit bio area, into oligomer self-assembly, and one of the things that we're doing with Dick Wolfson's group, he's now in Bristol, is looking at how we can get peptide oligomers to actually self-assemble into various sort of arrays. First of all, in one dimension, and that's what we're working on at the moment, but the aim will be to make oligomers which have this sort of structure, and if we can do that, we should be able to get the whole thing to assemble into a 2-dimensional array. So my present sort of area, which I don't know anything too much about at the present time, but I'm trying to work on it, is how can we get a 2-dimensional array? And the first one that we've got is a set of metal clusters. This is an open framework structure of nickel clusters, which we'd like to put onto a thin film surface. But at this stage, we can get it to make little flakes, but we haven't yet been able to get it to lay down. But I think we shall, within the next few months, get it to lay down onto a single surface. So these, let's get back to this, and then get to the last part of what I want to talk about. So that's what I'm doing at the present moment in Florida. The last part of my talk, I want to make some serious statements for younger people who are going into the sciences, and because we need you. And I think it's the sustainability issue. I think the fundamental sciences of sustainability are molecular sciences, chemistry, molecular physics, biological chemistry, nanosciences. I think the only show in town. And my primary high sustainability technology is basically splitting water into hydrogen and oxygen. I think Jim would probably agree that it's pretty high on the I've had a lifetime fascination with graphics, and this is I think this is my favorite picture of the sun. It's from Queen magazine. It must be about 40 years old, and I've kept it all this time. This is where all the energy comes from. And we're using, about 1 million years worth of fossil fuel every year. As you put the gasoline in your gas tank, you're putting dinosaurs and pterodactyls and whatever else in there. Unless you're sort of from Kansas, you probably I don't know what you're putting in there. But anyway, whatever. But every time I put gas in, I just think those beautiful animals. But basically, what I've invented, and someone told me that they're using it, is a sustainability quotient. And that is that everything we make, we should have a scale of +10 to -10, okay? Now, what do I mean? If we make industry put a sustainability quotient on everything that they make, then and tax it. That's, what do I say? Well, what about refrigerators? I put that as -2. Airplanes, -4. Central heating, -5. Cars, -5. SUVs, -7. Pickups, -9. Mack trucks, -10. A Ford Explorer got 3.7 miles to the gallon in New York, okay? Because, it's stopping at all those red lights. Anyway, so the idea is this, that we now have to look at sustainability issues from quite a lot of angles. And let's take yogurt, okay, as an example. Local yogurt, my mum made it, right? But you can get yogurt from France. How did it get here? Got on a truck, on a ship and whatever. So we're going to have to look at that. And I think these issues now are going to be rather important. I only make one exception, and that's mozzarella from Italy. I don't think anybody else can make mozzarella di bufala. But these are issues that I think we're going to have to think about. Okay, so we've got this wonderful world, and it's very beautiful from out there, but for how much longer? And this is now my favorite animal. Does anybody know what it is? Wow, yeah, it's the dung beetle. Okay. And that, it's estimated that if there were no dung beetles, we would be about 100 feet deep in elephant crap. Okay. But the problem is, what are we deep in? Well, if we take a beautiful field in England, well, it was a beautiful, not very green. This was in the newspaper, I think, last year, and we're looking at 40,000 refrigerators. This company was supposed to be recycling them, and it had 3 fields, and it had about 140,000 refrigerators just dumped there. Now, they're all in one place, so they have an effect, but you've been everywhere around, right? The world, right? You've been on a plane or on the train, or you've seen what's been dumped there. And that's our crap, okay, which is not easily recycled. So I've got a new, I design logos as well, and basically this is my logo and we really need to work out how lots of things, not just new technology, but actually recycling these things, and those are the problems. And we want young people to be involved with that, but there is a problem, and it's a language problem of science. At this meeting, at a Faraday discussion meeting in Birmingham in 1954 on the study of fast reactions, the German scientist Manfred Eigen asked the Oxford Don Ronnie Bell how the English language would describe reactions which were faster than fast. Ronnie Bell replied, "Damn fast reactions, Manfred. If they get faster than that, the English language will not fail you. You can call them damn fast reactions indeed." Now, I think that's a beautiful example of English. It's difficult to translate that, particularly into Japanese, where I was. But in fact, here's another bit of language. And in fact, this equation was in a paper by John Maynard Smith, also from Sussex, an absolutely fantastic guy. And he sent it off to a journal, and it was turned down. And he rang the editor up, and the editor said, why did you turn it down? He says, well, it's a bit complicated. He said, well, do you need this equation? And John said yes. He said, well, why don't you simplify it by cross-multiplying the D's? A little knowledge is a dangerous thing. Okay. Anyway, so there is a language issue. And in fact, I showed this, and an American professor came and I said, I'll tell you another story. He said there were 2 mathematicians in a restaurant, and they were discussing calculus and the fact that nobody knew any, and oh yeah, they do. No, look, no, yeah, they don't. So he said, look, I'm going to go to the washroom. When I come back, we'll ask the first person we see the simplest possible problem in calculus, and I guarantee they won't know it. $50 on it. Okay, so he goes off. Whilst he's away, he calls the waitress over. He says, look, when my mate comes back, you come immediately to the table and he'll ask you a question. You won't understand it, but don't worry, I'm going to tell you the answer. The answer is 1/3 x cubed. So she looks at him. What? 1/3 x cubed. Say it. Oh, okay, 1/3 x cubed. So he goes away, the guy comes back, sits down, and the waitress comes over, said, we'll ask the waitress $50 on it. What's the integral of x squared? And she says, 1/3 x cubed. He looks at her, he can't believe it. He says, he's just about to take, and then she comes back to the two of them and looks at them in total disgust and says, plus a constant. It's a bit of political commentary in there as well, but now I happen to think that's one of the funniest jokes I've ever heard. I don't take the credit for inventing it, it's just a wonderful one. But it is a language issue, okay? And so we have to recognize that to actually get deep into science, there is something we have to learn the language, and it's not so easy. If you want to understand Japanese culture, you have to learn Japanese. If you want to really understand English culture, you have to learn some English to understand Shakespeare and these things. So deep in science is this. And so although we can do something, I think people who have to make decisions on science have to meet us halfway. So the politicians and journalists really need to know a bit more science, I would say, than they in general do. And here's some reasons. Senior nurses discuss the problem stemming from nurses' inability to do simple maths. They put decimal points in the wrong place, so patients might receive 10 times more or 10 times less medication than intended, if you're lucky. A friend of mine was in hospital. He said he heard one nurse ask the other one how many milliliters there were in a microliter. Could be out by 10 to the 6, you know. So these are the sorts of issues, and they are serious. And in fact, there was recently a nurse administered 10 times too high a concentration of salt solution, and the patient died. So it's not totally funny. And in fact, I would say to you that if you go into hospital, you better have a little mass test out there and give it to whoever's looking after you. And if they can't get the decimal point in the right place, you better go to another hospital, because these are serious issues. Okay, so that's to some extent. There's another problem with young people. The fact is that this is a typical scientist, according to the media. Now, I know it looks a bit like me before I had my hair cut and took my glasses off. But the point is it any wonder that our kids don't want to look like this? Or this is the icon that the media have. And we do ourselves injustice as well. And in fact, where does it come from? And can scientists shake off their mad media image, okay? And where does this image come from? Here's the culprit, okay? Now, some of you might think this is the guy who, well, what do you think this guy did? Someone tell me. Anybody? Okay, well, you're wrong. All of you are wrong. This guy's an imposter. He didn't do any of those things. This is the day that I tell you that the guy what did it was this guy. And in fact, it's almost impossible to get a picture of him at the age that he actually made those wonderful discoveries. He was 17. If someone told me he was even 13, asking questions of what it would be like to travel at the velocity of light. It's young guys like this, not guys, old geezers like me are way past it. He was way past it then. And I think that's a problem. And in fact, these are the young students, Jim Heath, Sean O'Brien, Yuan Liu, and Jonathan Hare, who worked with us on the discovery of C60 and the work that we do. In fact, Jonathan now is a celebrity. How many of you watch Rough Science? Okay, he's the best guy on that. And actually, they wanted me to be on that. I thought, no way was I going on this and looking stupid, you know. But Jonathan was a student of mine. I got him to go on this. It was a great decision because he's a star of that program. It reminds me that I think the Royal Society rang me up one time and said, would I be on University Challenge? I said, no way, right? You know, I've sat there and I said, I know this, I knew this once, and even if I know it, I can't actually spit it out fast enough. And I remember seeing what it said the next day or two. It said, the Royal Society, I think some of my colleagues weren't as smart as I was on this one. They agreed to do it. And it said they couldn't even get the answers right when the audience was shouting it out because they were too deaf to hear. I thought, well, good thing I wasn't on that one. But anyway, but the problem is that these young people aren't the icons. It's people like this guy. And he's a Scientologist as well, okay? Anyway, so that's the problem. I'm now working, I've set up a studio in Florida to do workshops and on the web. And this new technology, which I really think we should embrace and get involved with. You can put the PowerPoint on one side and you can put the videos on the other. So the PowerPoint can come down in high resolution, and so you can do workshops all over the world. And I've done one to Venezuela about a few weeks ago, and I did a presentation of a similar lecture to this to Oxford about 3 weeks ago from Florida. I've done them to Iceland and all over the world, and I just can't go to all these places. And I'm trying to get the scientific community in particular to look at the way the internet can be used to help teachers teach better. And if we get a television set into every village in the world, we can surely get the internet into every school in the world and give the teachers access to the best teaching material in the world, okay? Wikipedia's shown what you can do, and if we as a community can get together and do this, then I think we'll actually really make an impact on young people all over the world. And in fact, I have set up the Vega Science Trust some years ago. It's on this website. We've got discussions, lectures, careers programs, interviews, and workshops, teachers' resources, and major issues. We've pioneered a new concept in TV debate that participants should actually understand the subject. We've got snapshots programs. We've got programs on DDT. In fact, this is man's greatest enemy. The embargo on DDT, which looks as though, well, I think the World Health Organization just repealed it, has actually, we can think of it really of causing the deaths of the order of 1 million children a year in South Africa. That one embargo. Something like 1 to 2 million children die from malaria in South Africa every year. And this is a factor of 10 higher than it was. We've got Max Perutz, and we've got Joe Rotblatt. If you want to see a great guy, well, Max is too, but Joseph is the greatest guy I ever knew personally. Worked for most of his life to stop the spread of nuclear weapons. An interview with him.
I've told you, and you have
also,
to believe that I
Bill
tell
Klemperer.
you the truth, that carbon monoxide is the second most abundant molecule in the universe. And yet, our theory, our equilibrium theory, says there shouldn't be one molecule in the whole universe. It's that extreme. What does this say? Well, it doesn't say that thermodynamics is wrong. Of course it isn't wrong. That's impossible to be wrong. It says that it's totally inapplicable to the chemistry of the interstellar medium, that everything is dynamical, that in a sense it very much resembles the Earth. If you ask, what is the equilibrium status of everything is quiescent, everyone's dead. That's it. And very uninteresting. So we would like something much more dynamic than the thermodynamic equilibrium. And I should say, as a testimony, really, every time I mention that to a group of college students, the audience breaks into tremendous applause if thermodynamics is not applicable. And I wonder why. It might well be that it's so poorly taught that they're just delighted that it doesn't work.
I thought this is one of our programs, a little bit from Bill Klemperer. I think the best lecture I've ever seen personally. I think Feynman's probably the best I've seen, and Bill's the best I've seen personally. And when he came to London, I got him in at the Royal, the RI, Royal Institution, and we recorded one of the great guys. Not only that, I did a whole set of those, and another one's this one.
As you see the skull and the head go transparent, revealing the outside of the brain, perhaps you can get a sentiment of the power of the technique, because now we're visualizing those water molecules that have memory constants characteristic of brain rather than facial muscle tissue. Well, our resident skeptic may say, look, you could do that on the slab in a post-mortem room, but I'd like to hope I can be forgiven for not submitting myself to the inconvenience of that particular experiment. Anyway, it's bad practice to teach graduate students to do experiments that they can't repeat several times.
I thought you'd like to see some of the extracts. I haven't been making those programs for a long time. I want to do something much less expensive, and this media site, this sort of technology now with a small studio, we can do it very inexpensive. Those programs cost between £10,000 and £20,000 for one program. We had 4 cameras, and we've made about 110 programs altogether. Those have been shown on the BBC, 55 have been shown on the BBC. So I know all about that sort of thing. Okay, so in the States now, and I thought I'd learn a bit. I've been looking into a bit about Jefferson and, well, Benjamin Franklin and Thomas Paine, who actually lived for quite a long time in Lewis, where we live. But I thought I like these guys. The founding fathers of the USA were a fantastic bunch. And they put into place secular safeguards for democracy, which are incredible. And I think there's certainly a problem today as I see the secular democratic principles being subject to harassment, if nothing else. But I thought I'd show you this. I have a wonderful colleague at Florida State, Michael Kasher, who some of you will know. And he came in one day and showed me a page from this book. And it's basically about Benjamin Franklin. Franklin wrote of a missionary who told the Susquehanna Indian tribe the story of Adam's fall and how it had led to Jesus' suffering and death. When he had finished, the Indian orator stood up to thank him. Franklin related with a twinkle in either his own eye or the Indians. I thought I'd show you. There's obviously a twinkle. It's a great painting of Benjamin Franklin. In fact, I think we're going to the Benjamin Franklin house, or tomorrow. I'm going to visit. Anyway, what you've told us, says he, is all very good. It is indeed bad to eat apples. It is better to make them all into cider. And I think that's what America certainly was, is a place, a great country, but also a great sense of humor, which I'm worried about it losing. But anyway, don't want that, I want this. A couple of years ago, I was in California and found this poster, and I wanted to share it with you because it's my favorite, one of my favorite posters, if not my favorite. It says, "I am an alien creature. I was sent from another planet with a message of goodwill from my people. The message says, dear Earth people, when you finally at last destroy your planet and have no place to live, you can come and live with us. And we will teach you how to live in peace and harmony. And we will give you a coupon good for 10% off all deep dish pizzas too. Sincerely, Bob." What I love about this is 2 aspects of what I think is important in life. And the first is that to recognize that we've got some serious issues for our grandchildren and our children. I always say, you know, I'm going to be well out of here when the shit really hits the fan, basically, but our children won't. But also, this guy has a sense of humor. And I think without that, I don't think there's any point bothering. I think we've got to retain a sense of humor. And if we don't, well, let's not bother, Jim. It's not worth it, really, saving them. But anyway, I think many of us in the sciences, we work pretty hard educating and reaching out to young people. And in fact, my favorite bit of film is this one.
I walk the maze of moments, but everywhere I turn to begins a new beginning that never finds a finish. I walk to the horizon, and there I find another. It all seems so surprising, and then I find that I know. You go there, you come forever. I go there, it's my way. We stay anywhere. The moon upon the ocean is swept around in motion.
Well, that is a group of kids in Mexico where I did a workshop with 300 of them, and it was just fantastic. I mean, I never tire of watching those beautiful kids having a great time. They learned some algebra. In fact, I did one with Manchester United. The original plan was to get David Beckham to help me teach the kids algebra. That's the real reason he moved to Real Madrid, but no, it was all planned, and it was really sad. We would have had all the cameras in the world, but we did actually work with O'Shea and Diego Forlan, and they helped teaching the kids algebra and numbers and stuff like this. And I think we've got to work with people that are iconic people to actually get kids to be interested in science. I've done it now with the Florida State football team. Anybody knows that, Florida State has a big football team, an American football team. And they helped me, and they were delighted because they'd never worked with small kids before, and they realized these kids liked them and they could do this and that. And I think we've got to make an effort. And one reason is that those kids in Mexico were the first people to find a use for my molecule C60. Thank you very much.
You've been listening to a special lecture vodcast from Imperial College London.